Hi guys, hello, welcome to this video where we're going to take a look at a problem that I've taken from a sixth term examination paper. So we're going back to 1987 here, step 3 from 1987, and it's question number 4 that we're going to be taking a look at. So I'll leave a link in the description to this video so you can download the past paper so you can see the problem for yourself, because there is a diagram associated with this problem and I've tried to reproduce it here on the board. But if it looks a bit wonky, that's because it is. So I would recommend that you download the paper for yourself. So let's get stuck straight into the problem. Now, because it's step 3, it's going to touch on kind of further mathematics material to a certain extent. So involved in this are going to be inverse hyperbolic functions and hyperbolic functions, volumes of revolution, which are on some exam boards but not other exam boards on the current specification. So we are going to be involved. That's going to be involved in the solution to this problem. So there are some things, because we're going so far back and the specification's changed over time, there are going to be some things that are involved here, some techniques that are not on the current specification for maths and further maths. Nevertheless, my recommendation is that if you are preparing for a step exam, if you're preparing for an MAT exam, that you do try to look beyond the specification and be prepared to learn some non-specification material. What that is, I'm not going to tell you exactly what to look at. It doesn't really matter, but just be prepared and open-minded enough to consider things that are not on the specification. If it is something that bothers you, if looking at non-specification material bothers you, think very carefully about whether a step or an MAT is the kind of exam that you want to be having a look at. Okay, so this is the diagram. I've actually missed a little bit off here. Okay, so the information that we've been given is that two funnels, A and B, have surfaces formed by rotating the curves y equals x squared and y equals inverse sine of x, 2 inverse sine of x, for x is greater than 0 about the y-axis. The bottom of B is 1 unit lower than the bottom of A. That's this distance here. And they are connected by a thin rubber tube with a tap in it. The tap is closed. A is filled with water to a depth of 4 units. Okay, so initially, depth of 4 units. We'll make a note of that. The tap is opened, and when the water comes to rest, both surfaces are at a height h above the bottom of B, as shown in the diagram. Show that h satisfies this equation. So the equation is h squared minus 3h plus sine h equals 15. Okay, plus 15. So we're not asked to solve this equation, we're just asked to show that h satisfies this equation. So it's a fairly straightforward problem. Okay. Compared to some of the other problems that are on this step paper, this is much easier. This is amongst the easier ones. Okay, so the first thing we really need to do is to figure out expressions for the volumes of revolution, because we're told that these funnels are formed by rotating these curves about the y-axis. Okay. So how do we find volumes of revolution when we're rotating about the y-axis? Remember, it's the integral of f of y squared times pi dx. Okay? Is that right? Sorry, dy. dy. I knew something was wrong. Okay? Remember, we've got to take into consideration the fact that we're rotating about the y-axis. Okay? Or in other words, another way of writing this would be pi the integral of x squared dy, where x is a function of y. So what that suggests is that we need to be finding x as a function of y. we're also told that x is greater than 0. So x is going to be equal to the positive square root of y here. And over here, x is going to be equal to sine of y over 2. Hyperbolic sine of y over 2. Okay, so let's have a look then. So the integral, so let's have a think. The integral from 0 to t, so I'm just going to use t as a dummy variable, of square root of y squared dy times pi. So what this will do, it will find the volume from the bottom of the curve here to a height of t, because I'm going to need to use different values of t at different times. It will find the volume of the funnel up to that particular height. Okay, t, whether it's 4, which is the starting depth, or whether it's something to do with this h minus 1, presumably. So let's have a look. What do we get? So this is going to be equal to pi times the integral from 0 to t of y dy. That's nice. Which is pi y squared over 2, 0 to t, which is pi y squared, pi t squared over 2. Pi t squared over 2. Okay? So initially, therefore, we're told that the water is a depth of 4 units, and that's 4 units in the funnel A. Okay? So when t equals 4, we get that the initial volume is equal to 16 pi over 2, which is 8 pi. 8 pi units cubed, or whatever. Okay? Just replace the t with 4. That's the initial volume of water. So now it would be good for me to have the volume of revolution of this thing. And in fact, I'm actually going to go straight into h for this. So the integral from 0 to h of pi times, what is it? X squared, so sine squared, y over 2 dy. Okay, so I think we're going to need some hyperbolic identities here. So what's a useful hyperbolic identity going to be? I know that cosh 2y is equal to 1 plus 2 sine, 2 sine squared, let me change that to theta. Cosh 2 theta is 1 plus 2 sine squared theta. Okay, so that means that cosh, putting it in terms of y now to fit this problem, cosh y is going to be equal to 1 plus 2 sine squared y over 2. So therefore, sine squared y over 2 is equal to a half cosh y minus a half. So plug that in here. So this is similar to what you might do with integrating trigonometric functions when you want to integrate sine squared x, for example. You typically use a trigonometric identity, cos 2x is equal to 1 minus 2 sine squared x, rearrange and so on. A similar kind of thing, just be careful with the identities. When you've got a product of, for every trigonometric identity, there's a corresponding hyperbolic identity. And when you've got a product of sines, you change the sign, the sign sign. So cos 2 theta equals 1 minus 2 sine squared theta. Cosh 2 theta is equal to 1 plus 2 sine squared theta. So it's Osborne's rule or something like that. But it's because of the way that sine can be defined in terms of complex numbers. So sine theta is e to the I theta minus e to the minus I theta over 2i. So when you multiply them, when you square it, you get in the denominator that 2i squared, or in other words, minus 2. Okay. So this is going to be equal to pi times the integral, pi times the integral from 0 to h of, might as well bring that out, cosh y minus 1 dy, which is pi by 2 integral of cosh y sine y minus y between 0 and h, which is pi by 2 sine h, confusingly, minus h. Okay, good. So therefore, we're told that this initial volume of water, eventually, when it settles down, when it's allowed to find its own level, when this tap is opened, it comes to rest, and both of these surfaces here are at the same height, h, above the bottom of funnel B. Now notice that the funnel A is, the bottom of funnel A is 1 unit above the bottom of funnel B. So if this height here is h, this height here is going to be h minus 1. Okay, so that means that the total volume, 8 pi, and it's a thin, let me just look at the details that we're given, a thin rubber tube. What that means is that we don't have to worry about any volume of water that might be contained within this tube, because it's a thin tube. Okay, in other words, its volume is going to be negligible. Okay, it's just a modeling thing. Okay, so this is going to be equal to the volume of the water in here when it comes to rest, which is this, pi by 2 sine h minus h, plus the volume in here. So that's going to be when t is equal to h minus 1. So it's going to be pi over 2 h minus 1 squared. Okay, so that's the volume in funnel B, volume in funnel A. That was the initial volume. Obviously, no water's been added, no additional water's been added, no water's been taken out. So we get 8 pi. Actually, I can cancel pi here. Cancel. And I can also multiply through by 2. So I get 16 is equal to sine h minus h plus h squared minus 2h plus 1. And what does that give me? H squared minus 3h plus sine h is equal to 15. Which, is that what I wanted? Yeah, it is. There we go. Okay, nice, easy, straightforward problem. Really no problems with it. Actually, I did have a bit of a problem with it. It was because I just made an algebraic mistake when I can't remember exactly what I did, but it was, these things happen just with the algebra somewhere. I'd forgotten, mucked up a sign somewhere. I can't remember what it was. But really, in principle, there's nothing difficult about this problem. Just remember, when you're doing volumes of revolution, pay attention to whether you're rotating your curve about the x-axis or about the y-axis, because you've got to take that into consideration. If you haven't done volumes of revolution, they're not difficult. They're really not difficult, and it's well worth having a look at them. Okay, and that's it. Okay, that's the solution to this problem. Please hit the subscribe button, hit the like button. If there's anything that you don't understand, please leave a comment in the comments section. Share this video with anybody that you think might find it useful. So what I'm looking to do is to reach out to people who are preparing for STEP exams, MAT exams, whatever, looking to go to university to do mathematics, statistics, whatever, and need some help with developing their knowledge and understanding of mathematics and developing their problem solving skills. I'm really wanting to get to those people to help them achieve their full potential. If you do need some help, if you feel that you need some help with your preparations for these exams, feel free to get in touch. I've got plenty of experience at providing tuition, support and guidance for STEP exams and MAT exams in university admissions for mathematics. I'm not associated with any universities, but to help with the preparations for interviews and things like that. I'd love to hear from you what your requirements are, what your expectations are, what you're hoping to achieve, and have a discussion with you about how I can help you. Okay, with that then, that brings us to the end of this problem, and it brings us to the end of this video. Thanks a lot for watching.